Hi folks, welcome to the presentation of a paper titled Re-IQA, Unsupervised Learning for Image Quality Assessment in the Wild. Image quality assessment is a challenging problem that impacts billions of internet and social media users daily. To advance research in this field, we propose a mixture of experts approach to train two separate encoders to learn high-level image content and low-level technical image quality features independently in an unsupervised setting. The novelty of our approach is its ability to generate low-level representations of image quality that are complementary to high-level features representing image content. We call this framework to train the two encoders as Re-IQA. For the task of image quality assessment in the wild, we propose to deploy the complementary low and high-level image representations obtained from Re-IQA to train a simple linear regressor to map the image representations to the ground truth mean opinion scores. Please continue to watch this video to learn more about our proposed method in more detail. No reference IQA for images in the wild presents exciting challenges due to the complex interplay among the various kinds of distortions. Further, due to the intricate nature of the human visual system, image content affects quality perception. A good example of this can be seen in figures 2A and B. Both images are captured by the authors on an iPhone 13 Pro and compressed using the same encoding parameters. While any distortions are almost negligible in figure 2A, there are artifacts that are clearly visible in figure 2B. Thus, image distortion perception is content dependent and heavily affected by content-related perceptual processes like masking. It is also well known that the perceived quality does not correlate well with image data metadata like the image resolution, file size, color profile, or compression ratio. Figures 2C and D show two exemplar distorted pictures from the in the wild scenario, one impaired by motion blur and the other by addition of film grain noise. These images illustrate the challenges of NR-IQA in the wild. Also, unlike full reference IQA that has access to pristine source images, no reference IQA lacks both information about the source images as well as the distortions applied. Because of all these factors and essentially infinite diversity of picture distortions, accurate prediction of perceptual quality of images remains a challenging task despite its apparent simplicity. Our method is inspired by the success of momentum contrastive learning methods in learning unsupervised representation of image classification. We engineer Re-IQA to learn content and quality aware image representations for NR-IQA on real authentically distorted images. A mixture of experts approach is used to train two encoders to learn high-level image content and low-level image quality features independently in an unsupervised setting. These representations from both the encoders are utilized to train a regressor that maps image representations to the ground truth mean opinion scores. The key contributions that we make are as follows. We propose an unsupervised representation learning framework for low-level image quality that are complementary to the high-level image content representations. We demonstrate that the combination of content and quality-aware features achieve competitive image quality predictions compared to the state-of-the-art methods. A major contribution of our work is that we propose a novel image augmentation and intra-pair image swapping scheme to enable learning of low-level image quality representations, which will be discussed later in this video. The dynamic nature of image augmentation prevents learning of discrete distortion classes and thus enforces learning of perceptually relevant image quality features. In Re-IQA, we use the unsupervised pre-trained MoCo V2 Resident 50 backbone as the content-aware module. The primary objective of MoCo V2 framework is to assign two augmented crops of the same image as positive pairs and crops from two different images as negative pairs. These positive and negative pairs are used to set up the info and CE loss, which is further used to train the networks. This setup works for high-level semantic image representations, but suffers a critical design problem. Two augmentations of even the same crops of an image have different quality and thus cannot be labeled as similar. Thus, this setup cannot be used to learn quality-aware features. We modify MoCo V2 as described next.
To train the quality-aware expert, we modify the MoCo V2 framework using our proposed image augmentation and intra-pair image swapping scheme. Based on our first hypothesis, two overlapping crops from the same image must have similar features depending on the minimum and maximum bounds of overlap. Crops from different images are marked different, independent of their distortion type. Crops with different distortions, augmentation, are marked different, independent of the crop locations. The augmentation bank comprises of 25 distortions applied at 5 different levels. For more details, please refer to the supplementary section of our paper. We create two chunks out of each training image, which consists of two overlapping crops from the image and their n unique distorted versions. Each chunk consists of images obtained from a single crop type. It is easy to see that the corresponding augmented crops are of similar quality as per our hypothesis 1. Next, we randomly swap half of the indexes between the chunks. The intra-pair swapping scheme results in the following pairs as shown in the right. This swapping construction encourages the quality-aware encoder to focus on quality, looking beyond content, as images with same content and different distortions are marked as different quality. We use backpropagation using the info-NCE loss to train the query encoder, while the weights of the key encoder are updated using the momentum update method. The overall pipeline finally looks something like this. We first choose two overlapping crops based on minimum and maximum overlap bounds. Then our proposed image augmentation plus half swap scheme generates and organizes the augmented images into similar and different pairs. These pairs are then fed to the respective encoders, which are then trained as mentioned. We conducted extensive ablation studies to find the values of the following hyperparameters. First, number of augmentations. Second is the patch or crop size. And lastly, the overlapping area bound. In the paper, we report the best values obtained for these parameters, along with the performance comparison among the various configurations. The content-aware model is trained on the ImageNet 1K database, which consists of 1.28 million images. For training the quality-aware module, we use a mix of multiple datasets to expand the range and variety of the training set. The mix includes 140,000 pristine images from the CADIS dataset, along with approximately 600,000 authentically distorted images collected from AVA, COCO, CERTH, and Pascal VOC. Images pass through the two frozen pre-trained encoders to generate image representations, which are then concatenated and fed to a trainable linear regressor. The regressor is trained by backpropagating the loss in the predicted quality score and the ground truth human opinion score. We evaluate our model as a no-reference image quality assessor on both user-generated content and synthetically distorted datasets. The following UGC IQA databases were used for the UGC evaluation case, and these are the synthetic IQA databases used in the evaluation. We recommend checking the table 2 of the main paper for extensive comparison of our proposed method with various state-of-the-art algorithms. Our methods perform at par with music, despite the fact that it is a transformer-based approach. Our model performs better than state-of-the-art methods on most datasets and competitively similar on the rest. Our method performs better than most when evaluated on synthetic datasets as well. Although it is quite interesting to note that for some datasets, quality-only expert performs better than the mixture of experts.
Next up, some results on cross-database generalizability. Cross-database generalization is a challenging NR-IQA problem. It is commonly observed that the model performance degrades when trained and tested on different datasets. The comparison of cross-database generalization of RICA with the state-of-the-art NR-IQA methods is shown in this table. As we can see from the results, RICA has superior cross-database generalizability. So in conclusion, we developed a holistic approach to NR-IQA by individually targeting the impact of content and distortion on the overall image quality score. We re-engineered the MoCo V2 framework for learning quality-aware representations by including our proposed image augmentation, overlap area-based smart cropping, and intra-pair swapping scheme. Results show that RICA consistently achieves state-of-the-art performance on 8 popular NR-IQA databases. Lastly, our method is flexible to encoder design architecture changes and can be extended to other CNN and transformer-based models. For more information about our work, please refer to the paper and supplementary materials. Thank you.